All right, so good morning. Right now we want to talk about Chapter 6. Chapter 6, you'll find that, it's basically extension or more realistic case of what you learned in Chapter 5. In Chapter 5, we learned about Newton's second law, Newton's first law, Newton's third law. And, in an ideal case, that is when there's no friction. Now, in Chapter 6, we're going to learn the case where it's more realistic. What happens to the object when there's a friction that opposes the motion, and what are the different kinds of frictions out there. So, what exactly is a friction? Now, we mentioned briefly in Chapter 5 that friction is always act in the opposite directions of the attempted motion. So let's say you have a floor, you have an object, and this object, without the external, so let's say just based on this diagram, we know that there's a gravity. That's mg, and there's a normal force. Now, let's say if you push this force, if you push this block with the force F, okay, and so the attempted motion is to the left. Now, let's say if you push this, if this is frictionless, if there's no friction between the block and the floor, then this whole thing will move, to the left because you apply force. And by Newton's law, you know that F equals mi. So there's a non-zero acceleration. But in real life case, you'll find that when you push something, it does not move. Why is that? Why does it not move? It does not move because there's another force that's opposing the motion, and that force we call that frictional force. Okay, so in this case, the attempted motion is to the left, which means that this this block is experiencing a frictional force that's opposing the motion. So the frictional force we call that F. Okay, lowercase f, and if it is not moving, we call that static friction. So we have the experience of static friction. Okay, so the static friction, just based on this diagram, because the whole thing is not moving, then by using Newton's law, F equals, so in the horizontal direction, if it's not moving, the whole thing has to be equal to 0, right? So if you look at this diagram, when you draw a free body diagram, so let me redraw the free body diagram right here. So a free body diagram, this is the object. You have a normal force upward, you have the gravitational force, you have the leftward force, the applied force F, and then you have the opposing the motion force, which is the frictional force. So that's your Fs. So just based on this diagram, we know that if it's not moving in the vertical, so these two forces have to be balanced each other. And in the horizontal direction, these two forces, they have to balance each other as well because it's not moving in the horizontal direction. So when it is not moving, the net force equals to 0, and the net in both directions, then we can deduce that the frictional force has the magnitude of the applied force. Okay, this is when you apply force and the whole thing is not moving. And then, of course, when it's not moving, if you want to, if you want to make the, move the block, you're just going to keep applying the force until at such point that this whole thing starts to move. When it starts to move, what does that mean? When it starts to move, it means that this force, this applied force, has the magnitude that is equal to the maximum static friction. Because this is a frictional for static friction, and there's a maximum static friction. So as soon as the force is greater than the maximum static friction, the whole thing is going to start to move. Okay. So when it starts to move, it means that the maximum static friction then is equal to the applied force. So you can see that when it's not moving or when it just starts to move, the applied force is exactly balanced by the frictional the frictional force, and those frictional forces are static, which means that the whole thing is not moving. Now, once you get this whole thing moving again, then it experiences a different a different magnitude of the force. It's still frictional force, but we call that kinetic friction. Okay. So one is, let's say the whole thing is now moving, and then it's moving in the leftward direction. Then the frictional force that it experiences now becomes the kinetic friction, Fk. Okay. So so the free body diagram should draw, based on this, because the motion is still leftward, so the kinetic friction is still, oppose the intended motion. So that's your free body diagram. So you have the mg here, you have the outward force there, you have the applied force that is to the left, and then they experience the opposing force, which is the frictional force. Now, because the whole thing is moving, which means that we know that, and that's with a non-zero acceleration, that it just means that this force, the applied force, has to have a greater magnitude than the frictional force. So if we assume that the positive x-axis is on the left, then you will set up equation by using Newton's law. The net force in the horizontal would simply be F minus the frictional force, and the whole thing is equal to mi. And when you do that, you'll find that your acceleration is basically in the same direction as in the directions of the net force. Okay, so this is basically how you calculate the acceleration when there's a frictional terms involved. Now in chapter 5, you don't have this term. In chapter 6, you introduce to this frictional force, which is more realistic because in everyday life there's always friction that's non-zero. So this is the friction that you have to take into account, and this is where it goes, when you apply Newton's second law. So these are just in symbol. So the question is, what is the magnitude? How do we calculate the maximum static friction? And how do we calculate the kinetic friction? Now, let's go back to the maximum static friction. Based on this diagram, we know that when in order to get the block to starts to move, the maximum static the applied force has to be equal or larger than the maximum static friction. So basically, I should write it like that. So the force has to be at least equal or greater than the maximum static friction. Then then it will start to move. Once it starts to move, then the friction force becomes the kinetic friction. So the question is, how do we find out the magnitude of the frictional force when it's maximum static friction or when it's kinetic friction? So in order to find that, this is how you do it. So the formula to calculate the maximum static friction or the kinetic friction is that the maximum static friction can be calculated using this. So we have the mu s times the normal force. So what is mu s? Mu s is called the coefficient of static friction. Now what about Fk? So Fk is equal to mu k times the normal force. So what is mu k? Mu k is called the coefficient of kinetic friction. Okay? So you have this equation to help you find the frictional force. And this is maximum static friction, and this is kinetic friction. So the mu s and mu k, they are basically a constant. So in order to find out the magnitude of this frictional force, you need the information of normal force. How do you find the normal force? Just based on the diagram here, you can see that based on this diagram, your normal force is just basically equal to the weight of the block. Okay, so this is how you find the frictional force, and there are two different kind of frictional force. Now, usually, that your Fk is less than the maximum static friction. The kinetic friction is less than the maximum static friction. So in other words, when you apply the force, when you apply enough force to overcome the maximum static friction, then it becomes easy to move the block. So you don't. So the friction force that experienced by the block is less than the maximum static friction when it's moving. Okay, so that's basically what it means. So this kind of friction is basically coming from the friction between the contact surface, and that we experience every day. There's another kind of friction that is also common as well, and that friction we call that drag force. The friction force we call a drag. Okay, so what is drag force? So drag force is basically you experience that when let's say when you jump off the plane on the parachute, then you feel the that you don't just go, your body does not just go go on the free fall because there's a parachute to support you. Now we're going to discuss what is the function for the parachute, and if you just jump off the plane without the parachute, you're just going to you're just basically like an object that undergoes the free fall acceleration, which that the impact when you jump out to the floor. Because of the acceleration that's downward, so the velocity at the impact, that's going to be large as well, which you don't want that. So that's why we have a parachute to help you to slow you down. So you can see that. So what slows you down is basically your air. The air is also slow, can slow you down. So let's see what the drag force is. So the drag force, we use capital D to indicate that's a drag force. So drag force, let's say you have, so what is a drag force? When there's a relative velocity, so the definition of drag force is that when there's a relative velocity between a fluid and the body experiences a force that opposes the relative motion and points in the directions in which the fluid flows relative to the body. Okay, so what does that mean? Let's say you have an object. Let's say this is the object, and it is in air. So when it moves downwards, let's say it moves down, it is moving down. When it's moving down, the air relatively is moving up. So the air is basically provide a drag force to support that. Okay, so you can imagine that when we draw a free body diagram, let's see how many forces acting on this object when it's flowing in air. So you have so this is the object, experience of gravity. The gravity does not change. It's just mass of the object and then times the gravitational acceleration. And then they also experience an upward force, which we call a drag force that's trying to slow it down. Okay. Now, this drag force, let's say initially this object is right here, and then when it's going further down, which means that the acceleration, the velocity increases because it goes a further distance. We found that the drag force changes magnitude, okay? And there will be at some point that the object moves so fast that the drag force will have a magnitude that exactly balances the weight of the object. So this is like initially, and then during the intermediate time, and then at some point, these two forces balance each other. Now we know that from Newton's second law, when there's a net force, there's a acceleration. So in other words, a net force in this direction, in the vertical direction, will be that your F net is equal to ma. So based on this diagram, let's say if we define the downward to be positive, then you have your mg. You have your mg minus the drag force, which we haven't had the expression for that. Let's just say there's a drag force, okay? And that has to be equal to the mass of the object times the acceleration. So there's a net acceleration, okay? And then so what we're saying is that this drag force, by experience, we know, it depends on how fast the object moves. The faster the object moves, the larger the drag force. So this is initially, and this is at an intermediate time that the object has acquired a substantial amount of velocity, and the drag force is also increases corresponding as well. And at some point, these two forces, when the velocity gets to a point that the drag force will have a magnitude that balanced by the gravitational force. And so when we look at this, when these two forces balance each other, it means that there's no acceleration, okay? So this is when there's no acceleration, this when they balance each other. No acceleration. What does that mean? If there's no acceleration, it means that velocity does not change. It can change because velocity, in order to change velocity, there should be an acceleration. So if there's no acceleration, velocity will not change. And when the velocity does not change, which means that the drag force will not change as well. So the whole thing becomes like moving at a constant speed. Okay? When it balance, it just means that the object now moves at constant speed. until you reach the ground. And that's why when you jump up the plane, you want to have a parachute, because that that can increase the drag force, so that you get to this stage much faster. And then once you move at a constant speed, then you can safely go fall down to the ground instead of like accelerating toward the ground. Okay, so the question is, what is the magnitude of the drag force? And we mentioned that the magnitude of drag force is not constant; it actually changes, and it depends on velocity. So what is the expression for the drag force? So the drag force has this expression. It's equal to 1/2, and then C rho A, and then V squared. So what is C? C is a coefficient, the drag coefficient, and it depends on the object and also the fluid. The density is what we call is the density of the fluid. Okay. For example, let's say in air is a fluid, so there's a density of air. So fluid density. What is A? A is cross-sectional area. So let's say this is an object, so this is effective cross-section area. So in this case, that will be from this point to that point. That's in contact with that's facing the when it's going down, the air is actually in relative going up. All right, and the V here is the velocity or speed. So that's why if you look at this expression, so you understand that why when the larger the velocity, you get a larger drag force, and that's because the drag force is a function of the velocity. So the larger the velocity, the greater the drag force, and so eventually there will be at some point that the drag force will be balanced by its own weight, and then the whole thing now will move at a constant speed. So the question is, what is that constant speed? And that constant speed, we have a terminology for that. We call that terminal speed. So what is that? What is the expression for the terminal speed when it's moving at constant? So the terminal speed, of course, or terminal velocity, that's basically is where the drag force is balanced by gravitational force. So you can set it like this. So and then plug in this equation here. So you have your 1/2. You have your 1/2 C rho, and then AV squared. That's equal to the gravitational force, which is mg. So you can calculate how what is the magnitude of that speed. So you have the 2 mg, and then over the coefficient, the density of the fluid, and also the cross-sectional area, and then square root of that. Okay, so it's basically how you calculate the terminal speed when you have an object that's that is going down and experience the drag force. Okay, so this is just like a common sense that. Not the common sense, but it's just something that you might experience. So it's nice to know. So you can see, in order to determine the velocity, you have to have the information about the fluid. You have to have the information about the cross-sectional area, and also the drag coefficient. Okay, and that's usually obtained through the in the laboratory. Okay. All right. Now the last one that we're going to talk about is the uniform circular motion. Okay, so in chapter 5 or chapter 6, chapter 4, we mentioned about when you have an object and it's moving at making a uniform circular motion. There's the speed does not change because it's uniform circular motion. Speed does not change, but the direction changes. If the direction changes, which means that there's a non-zero acceleration. So the whole thing here, when the object is moving in is making a uniform circular motion, it experiences acceleration, and that acceleration we call that centripetal acceleration. And if you recall, so something like this. And I think we derived the equation for the period. How long does it take to complete one revolution? We also we also have the equations for the acceleration. So the acceleration has the magnitude of the v squared over r. So this is centripetal acceleration that has v squared over r, and r is the radius, and then the v is the the velocity, and then your acceleration, the tangential centripetal, the centripetal acceleration, which is always center. The acceleration is always secant center. Okay, so the acceleration, the centripetal acceleration has a magnitude of v squared over r. So what does that mean when you have a non-zero acceleration? When you have a non-zero acceleration, we know that it experiences a force. So that force, again, Newton's second law, F equals ma. So you have this. It just means that the centripetal force will have a magnitude that is equal to the mass times v squared and then over r. So that's basically just that, okay? So this is another expression for the force when you have an object that's making the uniform circular motion. So the centripetal force is basically in the same direction as the centripetal acceleration. All right, so that concludes the chapter 6. And chapter 6, basically you want to learn the concept by doing problems. So I encourage you to do the problems from chapter 6.